Hi everyone, I'm Sumbul. Today I will present one of our recent works, namely a novel graph-theoretic deep representation learning method for multi-label remote sensing image retrieval. This work has been done with Begüm Demir from Remote Sensing Image Analysis Group of the Belgium and has been supported by IEEE grant Begüm. Here's my outline. I will start with introduction and explain the aim of the work, then go to the proposed method. I will give the experimental results and then I will finalize with conclusion and future ideas. As we already know that increased number of satellite missions provide significant growth of remote sensing image archives. And one of the most active topics in the literature is the content-based retrieval of multi-label remote sensing images from those large archives. Here you can see the illustration of image retrieval. It aims to find similar images from an archive for a given query image, and this is achieved by comparing image descriptors. And learning image representations is an important part of image retrieval, since it directly affects to obtain similar retrieved images accurately. And most of the recent image retrieval methods employ metric learning-based strategies for image representation learning. As an example, in the triplet loss-based approaches, image triplets, including anchor, positive, and negative images, are fed into the CNN that provides image descriptors. And triplet loss operates on those descriptors to learn a metric space where the distance between positive and anchor is minimized, while the distance between anchor and negative is maximized. However, the performance of existing metric learning-based approaches mostly depend on the accurate selection of image tuples, and this can be a very hard task for multi-label images. And these methods also don't take into account of multi-label co-occurrence and relationships. Accordingly, in this work, we aim to develop a method to extract and exploit multi-label co-occurrence relationships of multiple classes present in each image while characterizing the image semantic content. We assume that pixel-level labels of training images are available. And based on this aim and assumption, we propose a graph-theoretic deep representation learning method. Our method first represents each image with a graph structure that provides region-based image representation while using local information and related spatial organization. Second, it automatically predicts a graph structure of each image based on a novel region representation learning loss function to represent images based on the multi-label co-occurrence information. Here you can see the illustration of the proposed method. There are two main steps in our approach, in our method. First step, accepts the pixel level labels and create region-based representation. And second step, takes an remote sensing image and models multi-label co-occurrence relationships while describing the image content. I will be explaining each step in the upcoming slides. First step aims to describe regions associated to classes present in each training image. To this end, this step creates a graph structure for each training image. Each graph structure consists of nodes, edges, and weight matrices. Each node represents a region associated to a class present in the image. Since we have multiple classes in each image, there will be the same number of nodes with the number of classes present in the image. Here in the example, you can see that there are 5 classes and 5 graph nodes, since each class is associated with a node. And the edges between nodes represents the special relationships among nodes. Then the question is how we can define the edge weights. Actually, we define the edge weights by using 2 different information, and which is related with the special relationship of classes. And those information are class region sizes and the distance between them. And to find the edge between 2 nodes, we use 2 functions. Function S maps a class label into the size of the corresponding region based on the length cover map of the image. And function B maps the pairs of class labels into the distance between the centers of their regions based on the length cover map of the image. For normalization, we use the possible maximum values of those functions. By this way, if the regions are close to each other and their sizes are large, the weights assigned to the corresponding edges in the graph will be high. After obtaining the graph, resulting graph structure can be easily represented with an adjacency matrix. Second step aims to model co-occurrence relationship of multiple classes presenting any image in the archive. Accordingly, we propose a novel learning strategy to automatically predict the corresponding graph structure of any image in the archive while describing the complex content of each image by using convolutional neural networks. In this strategy, the characterization of an image is performed based on a CNN to model its multi-level co-occurrence relationships in the corresponding adjacency matrix. To this end, the prediction of the adjacency matrix is achieved by a fully connected layer that takes the image descriptor from the CNN and produces the vectorized form of the reconstructed adjacency matrix. Then to train the proposed method, we also introduce a novel region representation learning loss function. This loss function takes the adjacency matrix created in the first step and reconstructs the adjacency matrix produced in the second step and measures the error between them. Due to the proposed loss function, our method describes the content of a remote sensing image based on the multi-level co-occurrence information to achieve the region-based image representation learning. Because to construct the adjacency matrix, here actually CNN is forced to model this information while characterizing the image content. Let me give you the experimental results. Actually, we conducted experiments on 2 data sets, but in this presentation, I will focus on the LRCD archive because of the time limitation, but you can check the paper for all results. This archive consists of 2,100 aerial images, and each image has the size of 256 by 256 with a spatial resolution of 30 centimeters. The LRCD archive includes pixel-based labels in addition to multi-labels. Here you can see an example of images, their pixel-based labels and multi-labels. In this slide, you can see selected parameters and cross-validation is used to select them. For the backbone of the method, we use DenseNet 121 CNN architecture. We compared our method with CMS and neural networks trained with triplet loss and CMS graph convolutional network trained with contrastive loss. For triplet loss-based method, we utilize different triplet sampling techniques, which are random, batch hole, and hard techniques. To do experiments, we created the train, test, and validation secrets, and the training set is used to select query images, while images were retrieved from the test set. In this table, you can see the mean average precision results of all methods. One can see that our method provides significantly better results compared to all methods. The proposed method applies image retrieval more accurately compared to different sampling techniques of triplet loss-based metric learning or graph convolution network-based method, which also aims to model co-occurrence relationship. Here you can see the NDCG scores with varying number of retrieved images. Even with the different number of retrieved images, our method provides significantly better results. In this work, we introduced a novel graph-theoretic deep representation learning method for multi-level remote sensing image retrieval problems. We can say that our method is promising because of first, it accurately predicts graph structure of images, and second, it effectively defines image descriptors based on the multi-level co-occurrence relationships. It's also worth noting that our method requires pixel-level labels for training images. Such labels can be obtained via publicly available thematic products. However, these labels can be noisy. They can be incomplete, outdated, etc. And their use may result in uncertainty in deep learning models. Accordingly, as a future work, we plan to develop label noise robust graph-theoretic deep representation learning methods. Here's the end of my presentation. I will be happy to hear questions if you have any.